Hello everyone, my name is Luis Miras. Welcome to my talk, Other Wireless New Ways to be Pwned. This talk is going to have, we're going to have a live demo here. There's going to be some hardware hacking. We're going to be injecting signals into various wireless devices. And let's get started. So first I'm going to start out by saying what I'm not covering. Lots of other people have been looking at 802.11, other types of wireless stuff, and that's been done. I'm looking at something a little bit different. I'm not looking at Bluetooth, and I'm not looking at cell phone stuff. We're going to be this talk is going to be covering the other kind of wireless devices that we see very often. We're going to see RF wireless presenters, a couple different types. We're going to see wireless mice. Wireless mice, everyone's using them. There's some Bluetooth ones, but the majority of them are RF. And they're, as I'll show you later, there's no encryption. There's nothing going over the network over the air to authenticate them. So it's replay attacks can happen. Injection attacks can happen. This is very rudimentary type stuff. And being able to get access to the point of injection and the point to sniff is not that difficult. So part of this talk isn't so much showing these vulnerabilities, but kind of giving a tutorial on how you would do these types of attacks yourself, and how you can take a look at some of these hardware devices, and with very little amounts of hardware skill, you'll be able to implement these types of attacks. What I'm trying to do is bridge the gap between, most of us do a lot of software, and we can attack things over the network, we can write buffer overflows, we can do run debuggers, all kinds of stuff like that, and we're very comfortable with it. And for some reason, a lot of people are scared of hardware, but it's really the same thing. It's about putting the signals you want in the right places, and about being able to read what's coming out of a device. Same thing as writing an exploit for something else. It's just a little bit different technique to get there. And we'll do a little bit of overview on wireless keyboards too, and the differences between type of communication that happen between a wireless keyboard and wireless mice and a wireless presenter. So what's in common with all these devices? They're supposed to be low cost, but if you go to Fry's, you'll see a wireless mouse that uses RF, the same price as a Bluetooth one. The Bluetooth one has to pay licensing fees, has to pay for a chipset, so it's in the manufacturer's best interest that you buy the RF ones because they use very low quality chips. Most of the time it's one-way communication, and it's pennies on the dollar compared to Bluetooth chips. So there's no financial benefit for any of these manufacturers to create something secure. Even though there's been Bluetooth attacks, at least there's a base level of encryption and authentication. Whether that has been cracked or not, at least that's there. You're relying on something else rather than a proprietary protocol and algorithm, and security through obscurity, and hoping that no one's going to figure this out. All these are using what's called USB HID, which is human interface devices. When companies started making USB devices, particularly keyboards and mice, they didn't want to have someone have to install drivers over and over again. Oh, this doesn't work in Windows 95 when USB came out, or this doesn't work in Mac. They wanted it to come from a certain standard and be able to work across platform and across different operating systems. So they could develop the USB HID standard. This controls how these types of devices communicate and what type of functionality they can provide on your system. These are mostly using unlicensed bands, 27 megahertz, 900 megahertz. I've seen some at 49, 2.4 gigahertz. And even though it's 2.4 gigahertz, don't assume that that's going to be Bluetooth or Wi-Fi. It's still it's sped spectrum, but you can still access the chips and be able to read data off them. There's no encryption and there's no authentication. There's claimed ranges of about 50 feet. Just like we've seen with Wi-Fi, you can put antennas on any of this, and you're going to increase your range. You're going to be able to attack from greater distances. And especially if it's a 2.4 gigahertz system, you already have a CAN antenna. You can use the same antenna to be able to get longer range, to be able to sniff some of these keyboards or mice or what have you, and be able to inject traffic from further distances. Part of the problem with this type of attack is that you have to be relatively close. If you use something, an antenna, maybe some kind of a preamp, you'll be able to get longer distances. So let's start looking at some of the HID stuff. So HID generally means it's the USB HID standard. You can do HID over different types of protocols. It doesn't have to be USB. If you look at the Windows directories for their for their HID drivers, they can do HID over, I believe, serial, and I know they can do it over IRDA for sure, so over infrared, and over Bluetooth. There's a separate standard for that, but all these devices will communicate the same way. And so what does this define? This defines the way that the devices talk to each other. There's going to be a single host and a device. They talk to each other. They can't talk to anyone else. And the goal here is to not use any drivers. So that means that the device has to hold a description of itself, because the host doesn't know anything. So the device is going to hold the HID descriptor, and these devices are going to have very limited processing power. Usually we're looking at 8-bit microcontrollers. So even if you attempted to do authentication, you're not going to be able to do any real type of hashing or encryption with an 8-bit processor running at maybe a couple megahertz and possibly 256 bytes of RAM, maybe about 32K of flash. So on these devices, the microcontrollers, the RAM is usually just primarily used for the stack. You're not going to have any type of allocation. They're all written in assembly. Some of them in C, but there's no operating system. So they're just writing straight to the device. So even if you wanted to do this type of encryption or authentication on top of the channels that are provided, it's not going to work. That's why we have Bluetooth chipsets that offload all the processing and authentication to those particular chips, because the devices controlling them don't have enough horsepower. So these devices, what are the most common types? Obviously, there's going to be keyboards and mice. That's what the 99% of the devices are going to be. Something interesting is that most of the devices are going to authenticate or are going to claim to be a keyboard. It doesn't have to be a keyboard. It's just the way it communicates and the type of commands it sends. The wireless presenters, all they're sending are page up, page down keyboard commands. So when you plug one of those in, it recognizes it as a keyboard. Mice don't send key codes. They send movement. It could be relative movement, like when you use a mouse and you just put it down and you start moving it, it doesn't really matter. Or you can also have positional movement. Let's say a CAD drawing table or one of the drawing tablets, where every specific location is an absolute location in relation to the screen. And of course, there's buttons on top of that. So I'm going to take a look at some of the less common HID devices, just to let you know what other types of devices will be able to send this type of data. So we have the Power Glove. The Power Glove is a HID device. So if someone was using the Power Glove for something else besides playing with their Nintendo, they decided that it would be like super cool to use that as a front end to IDA, so you can like click around. You don't want to touch the keyboard. You want to click buttons on your hand and be super cyber. So you'd be able to inject keystrokes, whatever keystrokes they send, be able to inject those to that person. And then there's everyone's favorite, was the Wii controller, which also identifies itself as a HID device. Same type of thing here, except this device uses Bluetooth. So it does have an authentication layer on top of it. The other devices do not. But they all fall in the same category. Here's another HID device, Dance Dance Revolution. You could be playing Dance Dance Revolution against your friend and start injecting the wrong buttons, and they're going to lose. And they're going to lose, and you're going to look like this. So let's take some of these devices apart and see what's inside. Here's a wireless presenter. You're going to see basic patterns between all these devices. They're going to have kind of the same types of chips. Not the same chip, but the same type. We see here that we're going to have a transmitter chip, which is the one, the leftmost one that's circled there. And there's also a couple other chips. The bottom chip is the microcontroller, 8-bit microcontroller, like most of these devices. And we're going to see a serial EEPROM. So what's going on here? There's obviously the microcontroller is taking care of business. It's the one that sets up the protocol, talks to the transmitter chip. It's going to prep everything up and send it out. There's a serial EEPROM. That must hold authentication data. Even if it's just one-way traffic, it'll be maybe a serial number or maybe some kind of shared key that does not get hashed, because when we look at this chipset later, it's only one way. It's not a transceiver. It's only transmit only. So anytime you're transmitting only, if I'm talking across the room and I can't hear back, there's no questions, anyone can repeat what I'm saying. So there's right off the bat, we have replay attacks. Here's the corresponding dongle for that same presenter. And what we're going to see here is there's going to be a microcontroller as well that's going to double as the USB chip. So whatever data it gets and it decides that it's valid for that device, it's going to package it up in the USB packets and send it through your port, up through the host chipset, through the stack, back up to your computer. And here, again, we see the serial EEPROM. So this is the same authentication data. If you want to compare it to, let's say, like Bluetooth, these devices are paired at factory and cannot be repaired. And here's the receiver chip for the device. That's going to operate on the same band, and it's receive only. So once again, one-way traffic. Here's a Microsoft mouse. The microcontroller is going to be very close to the circuitry that takes care of the laser, that reads the laser. Then there's going to be, once again, a transmit chip and a serial EEPROM. And this is the dongle for this mouse. And we see a receiver chip. And there's the USB controller and the serial EEPROM that holds a 128-bit value, maximum, which means you can't buy a chip that holds less data. So it might not even be using 128-bit. The part of the problem, too, is you want your batteries to last a long time. You don't want your consumer to say, oh, the battery only lasts a week or 2 weeks because they're transmitting too much data. So when we're developing protocols, we want to transmit as little data as possible. They turn the transmit chips off when they're not sending data. So if you can, instead of sending a very long hash, a very long serial number, they're going to try to do it as least amount as possible, and it's limited by how many devices you want to not clash with. When we look at one of the devices, it'll say maybe it has 65,000 unique codes, which is it's a 16-bit serial number. So for the purpose of this talk and for the demonstration, I chose one of the devices to go through entirely, and this is going to be the Kensington Pocket Presenter. I chose this device because it's end of life, so hopefully not too many people get owned through this or the presentation's messed up. And by using an old device, if you guys want to try this, there's plenty of new devices, and go ahead and try a new one. Let me know how it goes. So this is the advertising talk here where it says you can transmit 50 feet away. All the information here pretty much highlights ease of use. It's lightweight. It's intuitive. It has a built-in laser pointer. No extra software. No drivers. 65,000 separate IDs. That's a lot, right? 16-bit, that's huge. And of course it works with Keynote because, we need Macs to be able to do their presentations as well. And actually for our demo, we'll be testing against a Mac. So this is some software that runs on Win32 computers. What it does is it hooks the USB stack, and when it sees a HID device, it's going to tell you the vendor ID, product number. And most importantly, at the bottom where it says collections, you're going to see generic desktop keyboard application. So it's identifying itself as a keyboard. So the first thing you do when you buy one of these devices, you look for the FCC ID. When any company in the United States is going to sell anything that transmits over the airwaves, they need to fill out an FCC application. They'll receive an ID if it gets approved. Part of the application process is submitting schematics, block diagrams, testing, pictures, external and internal pictures, and also where the labels go. They want to know where you're going to put the label. The label is very important to them. So the FCC provides this great website where you just type in the FCC ID. It's going to show you the application and all the files that they included as part of the application. There is an option when you're applying for an FCC ID to declare some of the data as confidential. And in this case, which is why I'm using this one as an example, Kensington did not apply for confidentiality on their schematic. So we're going to have part numbers that are standard parts, no custom parts. We have a schematic, and there's the schematic. This is for the receiver side. It has in the kind of center area, we have the three main chips that we saw on the dongle. All the way to the far side, that's the connector for USB. And on the left, I don't know what that is. That's probably something to cut down noise or something like that. It doesn't matter. There's no logic there. We're not really interested in it. And this is the logic for the transmitter. If you're not too familiar with schematics, just to go through it a little bit, obviously the yellowish rectangles, those are chips. If you go down towards me from the chip, you're going to see switches. So those are the switches on the presenter, which is sending input into that microcontroller. And all the way at the end, the little chip, that's going to be that's the EEPROM that most likely holds the serial number, so that the microcontroller can read the serial number and put its packets together and send them out over the wire. And we also have towards the bottom, we have our transmitter chip. So now we can start reversing. We got all the easy data that we could get, and now we have to see what is this device doing, how the protocol works. So we know that we have one-way traffic by looking at the data sheets of the chips, because they only transmit, it doesn't receive, or it only receives and doesn't transmit. Keyboards are the exception. Keyboards need to have two-way communication so you can light up the caps locks key, or the caps locks light, and things like that. These do not have standard protocols. Every manufacturer is making their own. That being said, there's probably only 3 or 4 of these that are really popular. So you'd only have to go through 3 or 4 to pretty much cover all the presenters. As far as wireless mice, I'm thinking that top 2 vendors are Microsoft and Logitech. And they're going to probably keep their data protocol the same throughout. We have varied frequencies. So we have, as mentioned before, we have ranges from 27 to 900, 2.4. Like the Microsoft keyboards, most of them are 27 megahertz. The device that we're going to be demoing, or I'm going to be demoing, is 900 megahertz, and some of them are going to be 2.4. So we're going to take a look at the receiver. This is the data sheet for the microcontroller. Publicly available data sheet is going to have all the pinouts. It's going to match to the schematic. You're going to be able to figure out certain types of modes by what some of the pins are tied high or tied low, if there's different modes. And you probably won't be able to dump the data from the microcontroller. These devices are usually one-time programmable, and they blow a fuse. There are ways to take off the layers, the coating, the plastic coating that's on the outside, and try to get into the chip, but it's going to be a waste of time. That's too much time. We'll be able to figure out the protocol and what it's doing without doing any of that work. And here is the data sheet for the receiver chip. And we take a look at the transmitter. And there's that's the receiver. And this is this is part of the transmitter data sheet. The best part of this data sheet is that second line. Applications, car alarm and home security systems. So people are using this in car alarms and home security systems, and it can only transmit, it can't receive. It can't authenticate. You can do replay attacks. And this is protecting someone's house, someone's car. I mean, if someone is looking at your I don't know, $20, $30 wireless presenter, that's fine. If you're spending thousands and thousands of dollars on a home security system, or hundreds of dollars on a car security system, I hope it's better than this. I hope they're not using this chipset in your car alarm. I'm sure someone hopes that they are, though. So here's a block diagram. In the middle, we have MCU is just shorthand for microcontroller. Up at the top, we have our EEPROM, which is going to hold our serial number authentication data. Our inputs, that's just a box that represents all the switches or buttons on the device. Doesn't really matter what the input is. It's going into the microcontroller. And then we're sending it to the transmitter chip. And the transmitter chip sends it up that piece of solder that represents an antenna. And there's the data. Here's the dongle. Once again, we have a microcontroller that also speaks USB. It has the EEPROM for the authentication. And there it has the USB port and the receiver chip. And the microcontroller is going to receive a bit pattern, just like the transmitter chip is going to receive a bit pattern, because these are digital chips. They're not analog. They're not going to send data out that is modulated. That's what the transmitter chip is for. So we'll be able to look at that in an oscilloscope, in a logic analyzer, or what have you, and we use that data to try to reverse the protocol. So if it's one-way data, one-way messages, it has to have the authentication data so that different devices don't get confused and talk to each other. So every packet has to have authentication data, and every packet has to have the data it wants the device to process. So in order to start tapping and looking at this, we want to tap right before the transmitter chip. We don't want to start tapping at the receiver because there could be noise, there could be error correction that's done by the microcontroller on the other end. So we want the cleanest signal possible. So we look at the input to the transmitter chip. After we figured out the protocol, we verify on the receiver end to make sure that we have the protocol right, because at the receiver end is where we're going to want to make a universal sniffer, so no matter what type of authentication data is coming through, we'll be able to listen to all the messages, basically like sniffing promiscuous mode on Ethernet. So here's the device that is coming off of the microcontroller. It's just tack soldered on there, little thin piece of wire. It's like 30 gauge. You just barely hold it on there and just tack it on. Excuse me. A drink of champions. For the purpose of the talk, I was trying to use pretty inexpensive equipment. So someone that is looking to get started in this can see that you can use inexpensive equipment. You don't have to spend thousands of dollars. This device here, I believe, runs say that $129. And actually, this is the same device that Joe Gran, which is in the front row, uses in his class. So if any of you took his class, I'm sure you recognize this oscilloscope. And here's what we get. You'll notice that the picture looks kind of weird because the parallax scope, it sucks. It works, but it sucks. So what I had to do is cut and paste the different sections together. That's why the bottom looks very weird. It lets you scroll the data, but it only lets you take a capture of what's currently displayed inside the scope window. That's just a software issue, and I wish they would fix it because this is not so cool.
How fast can that scope sample?
Joe? Not that fast.
Yeah, I think it can do 1 million samples a second for one channel and 500,000 if you're doing two channel. It's slow. Bandwidth is like 20 or 50K. It's slow.
So the type of data that we see with these types of protocols are usually about 10K. Like the standard PS2 keyboard, those have an internal clock and those transmit about 10K. So they're probably trying to emulate kind of the same types of speeds. And we see these different sections. There's obviously some kind of delimiters going on here. There's these big chunks of lots of activity and then more sparse activity in between. So the dense activity is the same. It doesn't change. So that must be some type of clock sync. The transmitter and the receiver don't know how long, let's say, like a high or a low is. So if you don't know how long it is, you could misinterpret something that was supposed to be low for two bits as 1 bit if you don't have some type of sync. So you're going to see stuff like this to see a sync. So it figures out, it syncs off the transmitter, and it's like, okay, the time period for a bit is this long because I've received so many patterns that are sent across, and then I can start processing the data in between. And that's the data. So we're going to take a look at this a little bit closer. And so you have a clock sync. After a clock sync, you're going to have to tell the other device some way of knowing, like, oh, get ready. This is going to be the data that's really important. You can't just start flipping bits because it might be part of the clock sync. So that's why there's that part in the beginning that has about 5 ones. That's telling the other side, hey, get ready. I'm going to send some data. And if you'll notice at the end, it sends about 5 zeros, and then that lets the other side know, okay, I'm done. You can go back to try to listen to a clock sync again. Here's the same thing in a logic analyzer. In the logic analyzer, it's going to tell you what the bits are. Don't be fooled that think that this parallax scope can do this. This is me inside of like paint.net clicking on there and typing zeros and ones so I can write it down. They don't do this for you. A logic analyzer will do that for you. It still doesn't know what the period is, so that's why there's the big sections of, let's say at the beginning, it says 1B for one binary, and it doesn't know that it's 5 separate bits. But the good thing is that you can take, for various of these tools, you can take the data and dump it into like a comma delimited file, and then you could do some kind of, if you wanted to, you could do some kind of heuristics on it and determine protocols that way. Or you can figure out the clock cycle and then run a script through it, and it'll dump it out for you. So here's the complete protocol, including what was decided was the header and the footer. These are the 3 buttons that come on this device. Page up and page down, that's to forward and, to go back and go forward on the slides. And hide, you push that button and it turns the screen black. So this data is obviously going to be some kind of header and some kind of footer. It doesn't affect our determining what the serial number or the key codes are. So we get rid of that. Now we do the most rudimentary of, I don't even want to say cryptanalysis because it's not cryptanalysis, but you just match what's the same and what is different. So these are common across all packets, so this is probably the serial number. And these are different, so these are probably the key codes. And this is the protocol. It's going to have a header. It's going to have part of the serial. It's going to have data, a little bit of data, some more serial, data, and then a footer. So what kind of attacks can we do against this? Well, we can do passive attacks, sniffing. We can get maybe some types of authentication data. Really, that only matters in keyboards. Trying to figure out if someone's clicking on stuff on a mouse is not going to get you anywhere. Trying to see if someone's using a presenter, you're probably in the room watching the presentation, so you know what they're doing. But you'll get the authentication data. You'll get the serial number, which you'll need in order to inject traffic. As far as active attacks, there's always denial of service, and then there's what everyone wants is execution of arbitrary commands on the target system. So how do we do this? We bring our own microcontroller. We're not going to use their microcontroller. It would be ideal if we could just reprogram their microcontroller and not have to wire anything up. But the problem is it's one-time programmable. So we can't even reprogram it. One-time programmable chips are way cheaper than flash chips. Flash chips are just used for development, and then once you have your code worked out to the point that you want, then you do a run on one-time programmable chips. And you can't even read them anyways because the security fuse is blown. And at this point, we already know the protocol, so there isn't anything that we need from that device. So RF is hard. Designing RF is hard. There are people that specialize in doing RF design, and they're great at it. I'm not going to be great at RF design. I don't care about RF design. I just want to send data. We don't need to even know about RF design. We don't need to have a scanner. We take over the OEM equipment. We take over the dongle, and we take over the transmitter. That already has a working receiver and has a working transmitter. So we're going to use those against the target. And what happens is if you start injecting data into the transmit chip and then you're receiving from the receiver chip, you've basically created like a metaphor of a network socket. You're putting data in on one side, and it comes out the same on the other side. So this is how we're going to sniff at the chip level. All we do is we're going to either cut the trace or the pin or the connection between the receiver chip and the microcontroller. There might be a way to put the chip into high impedance, maybe. I don't know. I just cut the trace. So in this picture here, the metal can on the left-hand side, that's going to be the crystal. Right above that, you'll see that there's a wire soldered onto one of the pins of the chip. And I have all this electrical tape on it because that's my protection from it ripping out, because you're soldering these little tiny things. So I usually use electrical tape around something to secure it down. Especially when you have these big floppy connectors, these clips, sometimes it can flip over and then it'll pull your connection off if it's not soldered properly. So this is how we start sniffing the data. And this is what we really want, is we want to send data. We want to inject at the chip level. So we're going to cut the connection between their microcontroller and the transmitter chip. This is a little fuzzy, but the wire that is coming straight out it cut the pin, and it connected via which is when you have like a dual layer board, just top and bottom, and you need to pass something across a path that's already been crossed. You can't cross it. So what you do is you run some copper, and then you make a hole and has copper inside of it, and then that connects to the other side, and you start passing back and forth. Those are great places to tap. They have a coating on it to protect it from corrosion or whatever, so you just take an X-Acto knife, kind of scrape that stuff off, and then you have a great location to solder wire on there. It's a hole, and it makes a good connection. The two wires coming off the top, I'll come back to later, but that's coming off the EEPROM, and I'll show how you're able to sniff traffic between the EEPROM and the microcontroller. So, which is good for different things, but we want to. There's a lot of data going across between these chips, and it might be useful to see what they're doing. So we have to do passive attacks because we need authentication data. Like I said, from keyboards, we might be able to get passwords or other sensitive data. Mouse data, not so useful. The type of active attack that we would do on a device depends on what hit type. The hit type limits the kind of data that is being passed up. So there's basically two types, keyboards and mice. A presenter is counted as a keyboard. So if we're able to inject complete keyboard commands, this is what I'm going to send. I'm going to send the Windows key plus R. And that's going to pop up on their box. Then I could open IE to a machine that I control. I could run a command shell. Then I could echo data to a BAT file or some other type of scripting. You could use like Windows scripting or what have you. And then you have some kind of logic. So you could check for certain things. You could check IP addresses. You could try connections. You could do different. You have a program basically, and then you would execute the batch file. Active mouse attacks. Well, there's going to be two types of mouse attacks. One is you can see the target. You can see the screen. You can watch the cursor moving along. And then there's going to be blind attacks, where you're just going to try to guess where to move the mouse to and start clicking to try to get some kind of execution or something. So one is we're able to see the screen, and the other one is we're blind. This is how, for either of those, how we're going to try to execute commands. Microsoft has accessibility, and we have accessibility for our attacker. This is a virtual keyboard. If we can figure out the layout, we can type commands. Every time you open this accessibility thing, it always goes to the absolute center of the screen. Even if I've moved it around, I tried. By default, it goes there, and then I was like, oh, I wonder if you used it and you close it somewhere else, is it going to open it up at the last location, or is it going to open it up at the original location? It always opens it up in the center. So now you have kind of a target of where you want to try to direct your mouse movement. So blind attacks, you have no visual feedback. You can try to make an educated guess. You can maybe you kind of know where the start button is going to be. It's going to be, you can move all the way to the bottom. Maybe try to move a little bit up. Click the start button and try to get to the run dialog, or try to get to the virtual keyboard. To really do this, you're going to have some kind of scripting language to be able to send this data. You're not going to be able to do this manually. So the problem with being blind is, how do you know if something works? You need some kind of feedback. So what I would do is you control a web server. You have a Trojan on there. You're tailing the logs while you're doing this attack. And if you see a connection coming from that box, you know you're successful. If you wait a while and there's no connection, then readjust your algorithm and try again, and keep trying again. And there's going to be tons of things opened up on this desktop, but whatever, doesn't matter. So let's take a look at the toolkit. What are some of the things I used to do this, and what are some things you can use to do this? So microcontrollers. I started programming microcontrollers a long time ago because I wanted to reverse engineer the original PlayStation mod chips. The stealth chip came out, and I was like, damn it, I can't play games anymore. People are checking for the standard chip, and the stealth chip is doing something different. So I started programming microcontrollers, reverse engineered it, and that's how I taught myself how to program these things. Originally, I started with PICs, and they served me well. And I was at CanSec, my programmer died, and then I was like, screw it, I'm going to try something different. So now I switched to AVR, and in some ways the development is better, because when you buy this board, it comes with switches, it comes with LEDs, it comes with a lot of useful stuff that you can just use right out of the box. You don't have to build your own circuit. The one I was using before was strictly just a programmer, and it wasn't so much a prototyping environment. This is just a screenshot of their IDE. Everything, at least for the simple stuff, I just use assembly for the chip. There are C compilers. I've never used them. And here's a pretty picture of the board, which is the same board I have up here. A logic analyzer. Logic analyzers will make your life so much easier. It'll be able to synchronize all these different signals at the same time. You want to establish some kind of relationship. Oh, this goes up, the chip enable goes up, then you get this data coming out. You have to establish these kinds of relationships to be able to properly debug and reverse engineer. Better logic analyzers are going to do some type of analysis on the data. You'll be able to set a type of interpreter on the data. So displayed as hex. Say this is an address, so you can group together, let's say 16 different clips that are on your address bus, and you'll be able to see what addresses are going across the wire, and it's going to provide you the number. You can also look at the data that's going across, and even better than that, you can have interpreters for these types of things here on the left-hand side. We'll go over some of these a little bit more, but look at the bottom. We have it'll decode RS-232 for us. That's great. We see the commands coming across. We don't have to look at bits anymore, and that's how it should be. I mean, we don't want to waste time doing that stuff if it can do it for us. And here is just connected to one single connector is hooked up there, and that was at the transmit data. And it can also be broken out into a table like this, where you have when the event was triggered, what values are coming across that. And if you look at the RS-232, I mean, we see line feeds there, we see commands. That's pretty cool. This is a really cool board. This is a microchip, a PIC but it's hooked up to USB. It already has a USB controller on it. It comes with firmware, and it acts as a serial port. So you connect to it, and you can turn on certain pins to be output or input. You can send data across it. So let's say you develop something on one of your boards that's going to take care of the low-level single banging, right? Then you want to control it from your computer. So you just hook this up and set the appropriate output pins, connect it to your other device, and it's all controlled from your computer now. The schematics are available. The full source code to the firmware is available. There's various kits. This one specifically here I bought from SparkFun. That place is great for doing prototyping, especially things like this that are like halfway there, that you don't have to do that much work. They have really good tutorials on doing surface mount soldering, beginning embedded programming for these types of chips. It's really like a hobbyist kind of store. They also, which is kind of cool, is they took apart that the Nike iPod thing that goes in your shoe and keeps track of you running and stuff. They broke all that out, reverse engineered it, show you what transmitter chips they use, and it's surprisingly similar to some of these presenters. Some of them, I think it uses one of the same chips as, I believe, the Logitech one. So here's some pros and cons of this. The pros is that it's cheap. The thing's only $25, and it just works. It has a large number of I/O ports. You can set some of them to digital or analog. And the firmware is well maintained. It's updated. There's full source to it. But the cons is its limited speed. Because it's operating as a serial port, it's not operating at the full USB 2.0 spec where you can transmit tons of data. This is transmitting at 9600 baud. So you're not going to be able to move huge chunks of data at any decent speed. And using the default firmware, you have no direct driver access. So the only way to use it is to connect to the serial port. So for high-speed applications, you're going to have to write a custom firmware. And right now, there is no public high-speed firmware for these devices. A couple of people have wrote them, but I think they're keeping them internally for like their company or what have you. So you'd have to write one yourself. So intra-device communication. This is a very popular two-wire communication protocol, I2C. It's used a lot for the serial EEPROMs. There's going to be a clock signal, a clock line, and then a data line. There's going to be master and slave nodes. There's addressing built into it. These are the types of speeds that you can expect through it, and you can connect tons of these together. 112 nodes are possible. And this is a more recent design. It went up to 10-bit address space, and a lot faster traffic can go through it. Common uses in these where you'll see them in certain types of devices. You might see them in NVRAM chips. Some DACs might have them. Super popular for serial EEPROMs and microcontrollers. The way that you can sniff this bus, you could do it manually with your oscilloscope, which is kind of a pain. You can use a custom microcontroller chip. I'll talk about that a little bit later, but this website, someone wrote some code so it sniffs the bus, and then it sends out serial data decoded, and then you can hook something else up to it. And then, of course, there's Logic Analyzer, which is if you have the money, that's the best choice. The other popular protocol, kind of serial protocol between these types of devices is SPI. And if some people have done JTAG, it kind of looks familiar. And that's because JTAG is kind of an application stack for SPI. But embedded systems from 8-bit AVR or Atmel devices, little devices, all the way up to ARM system on chips will use this bus protocol. FPGAs will use this internally because it doesn't use a lot of lines, and between your inside of your FPGA chip, you'll be using this to communicate between different parts. And of course, Flash and EEPROMs use this as well. So you could sniff this with an oscilloscope, but you're going to need at least 4 channels, 3 or 4 channels, depending on the implementation. Most scopes are just 2-channel. You could write your own code to sniff it with a microcontroller, or you could use a logic analyzer. And this is something that I've been starting to work on, is hardware level fuzzing. I'm able to inject into these chips. So there's probably some software problems in them as well. The software problems exist throughout programming. So if I'm able to inject into the chip, let's say into the transmitter, that's giving me direct access as a socket to the server, which would be the receiver chip. So your chip is at the low level. It's flipping bits on and off, so you just can set patterns to send out to that. And because these serial numbers and these command codes are so small, we're talking like 8-bit data spaces. That's only 256 combinations. You can fly through that, and that doesn't take that long. And then you can try to do send longer data than expects, and classic fuzzing kind of stuff. And just like you have the same constructs, you also have the same problems as software fuzzing. Here's another logic analyzer. This is kind of like your father's logic analyzer. No one has these anymore. So hardware fuzzing, detecting bugs can be difficult. These chips are black boxes. You're not going to be able to get inside of them. I can't hook up a debugger inside of it and see if there's an exception and, oh, cool, I have a bug. So you really have to try to correlate your data generation and your inputs and outputs to this chip to try to determine if anything went wrong. So in the example with a wireless presenter, when I was trying to fuzz it, what I would do is I only care about if it gets past the USB chip. So I'm going to have something that hooks into the USB stack, and if I see anything coming from that USB ID, I know something got through that it shouldn't. So that's one way to check. Obviously, that's at a higher level. There might be deadlocks and other problems at the lower level, but when I sent all the data, it kept working. I didn't find any bugs in this implementation. Here's something else that is really interesting in embedded systems, and specifically AVR chips. Other chips are vulnerable as well. But there are recursion attacks. And it depends on how the memory is mapped and the layout where everything is located in memory. So the problem is just like DOS, you have output ports mapped into RAM, and they're mapped into the lower parts of RAM. The stack starts at the top of RAM, and let's say you enter a function, and it's doing recursion, and you keep going, and boom, you just hit your out ports. Those are the actual pins coming off the chip. So you might cause, depending on your point of view, worst case, best case, you could possibly maybe cause a fire. I don't know. I thought about demoing that, but then I was like, Black Hat might not like that if I start a fire inside Caesar's Palace. But let's say it controls some kind of lock system, and you change the out ports to pop the lock because you found some kind of logic or parsing bug in some function that is causing it to lets you keep recursing through whatever input you have. So this is a little contrived. I don't have a valid in the wild test case or what have you, but the attack is valid. If you can control recursion through some type of logic bug or some type of parsing error where it keeps on trying to parse something because the parser is written wrong, there are embedded web servers for a lot of these types of devices, so you might have classic bugs that we've seen in normal computers. And then you can try to change the output with a return address. And just like Barnaby's talk, there's also a vector table located at the bottom. There's a vector table mapped from 0 on these devices as well. And all these assumptions that we made for general purpose OSs are not necessarily applicable to embedded. So these kind of things you have to kind of look out for, and it opens up a bunch of different attack vectors. And this right here is, if you start traveling with tons of electronics gear like this, and wires, and cables, and oscilloscopes and stuff, you're going to come across one of these little notices in your bag. It's a notification of inspection. I guess when I was leaving San Francisco at one point with all this stuff, they wanted to make sure that I wasn't carrying a bomb in my bag because they saw all this electronic gear. So that's just, in case you travel with this stuff, that might happen to you. So now I'm going to do a demo with Joe. You want to come up here? So on Joe's computer, he's going to be running a presentation. We have he has the presenter that goes with the dongle. It's all taken apart, obviously, because I take all these apart and I try to sniff them and whatever. And he has the dongle, the presenter that matches up to that dongle, and will show that will click through the slides. And then, give a hand to my lovely assistant. And closer to me, I have a presenter that's been taken apart. It's hooked up to the microcontroller here, and it's injecting traffic into the transmitter chip. So you want to switch displays?
Is that awesome? It's good. All right, should we try to use the manual control first?
Yeah.
I don't know what keys do what. But all right, there we go. Hi. Thanks a lot, you guys, for coming to my Black Hat talk. Welcome to my presentation.
Okay, so that was him using the original device, and now this device, I've rigged a bunch of the different switches to send different types of commands. Some of the switches go forward and back. There are switches that are set up that while you hold on to it, it'll just keep on sending forwards, and then I have another switch that you press it once, and it'll start sending, you press it again, and it'll stop. So I set my automatic command to just send tons of page downs, and took this flip book and made it into separate slides into the presentation. So you have something to look at while it scrolls through and injects into the receiver. It's a pretty long flipbook, actually. Can we switch them back? So as a summary, the first thing you want to do is look at the FCC ID, look up all the information you can get from their website. You want to tap into data path, reverse the protocol, hook up your custom chips, and start sniffing and injecting. And all that's going on here is we have client-enforced security. We're trusting the transmitter to send the appropriate serial number, and that's the only thing that's stopping it. One more thing I wanted to mention is once you start programming these chips, you can start making your own tools. You can. One thing I've been working on is making a custom sniffer chip. So when it sees that kind of clock sync, it'll figure out what type of spacing it is, and it'll start outputting the bits for me as a normal bit pattern, and then that'll be hooked up over USB, and I can basically, like a poor man's logic analyzer that auto finds the times and the time periods. So that's it. Is there any questions? Yeah, that's the first thing that I wanted to try. Obviously, if this supports a keyboard interface, that's what I want. You want to send keyboard commands. Unfortunately, it didn't work. I tried the whole key space, and no other commands went across. The actual amount of data that's going across the wire is very small, primarily because since it costs a lot of battery to send data, they're going to try to limit the amount of data, so they're not going to cover the whole key code space. So yeah, unfortunately, I wasn't able to do that. As far as the keyboards go, I've been able to receive data that is coming across, but I haven't been able to reverse the encoding that it's using yet. So along those lines, what I've done is kind of build like a proxy system. So I can get some data, modify it, and send it across and see what happens to try to reverse it. So fault inject some data and see if what happens on the other end, how it's interpreted. Any other questions?
Have you gotten to play at all with any of the infrared wireless microphones?
No, I haven't.
Wondering, a lot of times, a simple replay is all you need to want to replay unlock or something like that. But I haven't seen anyone present a sort of generalized record and replay that they all seem to go through the stage of decode the protocol and then retransmit, replay the instructions and re-encode. Is there some reason why folks aren't trying to do a more generalized record and replay? Is that technically hard?
I don't see why it would be, but that's where it's really like behooves you to have it hooked up to a computer so you can sniff, process data, and send the same data back out. Some of these more advanced logic analyzers are able to do data generation, which is what I'm working on myself to be able. I just want one channel to data generate. Something else to look at on the keyboards is, in that case, you really want to look at the traffic between the EEPROM and the CPU, because they actually do proper pairing. There's if it gets unpaired, there's a button at the bottom where you sync up the devices. So that type of data would be important too. So then you can see, they're doing a read from the chip and they're doing a write, and we know what value and what address, and then try to extract that from the data coming across. So that's another some more known clear text.
How much was that logic analyzer?
That one was 389, and it's 34 channel, and I believe it's 200 megahertz bandwidth.
Is that like a big cable with the
I have it right here. I can hold it up. So it comes with this. It has 34 connectors, and then you have to hook up something else to these pins. You can hook up clips like this, or it can go directly into some kind of header on your board. So a lot of times when you're debugging your board, you're going to have some type of header, so you just hook right in. Any other questions? Well, thanks for coming, and if you have other questions, just find me later. Thank you.